Recording. Okay, so I finished with the, so to speak, theory of Fourier transforms on the real line, and I was planning to go to some applications. Everything in the rest will be some applications, so to speak, unless I come back to just to tell about the locally compact abelian group theory. But except that, it will be all some applications to within outside mathematics. Yeah, but before that, are there any questions about this business, about Fourier analysis on the real line? Are there any general questions? Okay, so if not, let me go on. So there are several applications I could do. So I thought I will do one thing which is actually somewhat self-contained, and I only want to spend one lecture on it. It's an interesting one, funny one. There are even simpler ones which I will come to, like equidistribution and so on. So maybe I can mention some. I mean, one of the things that okay, I'll come to it when I come. So today we will just do one particular thing, which is Bernoulli convolution. I'm hoping to just finish it today. It's where, okay, what are Bernoulli convolutions? They are just convolutions of Bernoulli distributions. Okay, so let me write. So fix, what happened? Oh, my tablet is upside down. Sorry. Yeah, so fix, so let lambda be a number between 0 and 1. Okay, strictly between 0 and 1. And you define, and nu lambda is a probability measure. I will define it. It is the infinite convolution of the following. Okay, maybe since everyone here is familiar with probability language, let me first define it in that way. Nu lambda is the distribution of the random variable x lambda, which I define as epsilon 1 lambda, epsilon 2 lambda square, and so on. The infinite series, where epsilon and r independent plus minus 1 with equal probability. So each epsilon and independent. So you form this series with lambda, lambda square, lambda cube. Each term will be given a sign plus or minus 1 independently with probability half. So that is what x lambda is. So x lambda is a random variable. The convergence is clear, right? Because it converges absolutely. You put absolute values, it's lambda, lambda square, lambda cube, which converges because lambda is between 0 and 1. So we know that this converges. So that is a well-defined random variable, and nu lambda is the distribution of that. Okay, so why we call it Bernoulli convolution? Because each of this, so we can also say alternate descriptions. One is that nu lambda is the infinite convolution. You know, when adding random variables corresponds to convolution. What is the distribution of lambda epsilon 1? Lambda epsilon 1 is lambda with probability half and minus lambda with probability half, right? So let's write delta lambda plus delta minus lambda by 2. Convolution. What about lambda squared epsilon 2? That has distribution. It takes two values. I mean, it puts two values, lambda square and lambda minus lambda square with probability half each. And so on. You put lambda cube plus delta minus lambda cube by 2. So this is this infinite convolution. Okay, so an infinite convolution of Bernoulli. Each of this is a symmetric Bernoulli. Putting mass, if these points are going to 0, that's why the infinite convolution makes sense. So the series These things are going to zero fast. That's why it works. Now, this is not the only thing Bernoulli convolution is. Okay, but we'll stick to this one. Okay, we'll stick to this one. Another way is via the Fourier transform. If you look at nu lambda hat of t, since I use lambda for the parameter, let me use t for the argument of the Fourier transform. It is expectation e to the it x lambda, which is, well, everything is nice here. So we can get the infinite product. So we'll get, okay, n equals 1 to infinity. These are independent random variables. We'll get lambda epsilon to the power n. Now, lambda epsilon to the power n is, sorry, lambda to the n epsilon n. So is there a question? Lambda to the n.
No, I just wanted to point out that that's all.
Okay, yeah, thanks. So lambda to the n epsilon n, which is actually the Fourier transform of the particular nth measure here. So that is lambda to the n and lambda to the minus n with equal probability. So that is e to the I. Okay, I
That
forgot.
is a t also.
T. T and I. Sorry, I forgot that. So let me just write it properly. Expectation of e to the I t epsilon n lambda to the power n. Now that is e to the it lambda to the n plus e to the minus it lambda to the n by 2. That's the Fourier transform of that, which is cosine of t lambda to the power n. So that's the infinite product. Now let me just write it here. This product n equals 1 through infinity cosine of lambda to the power n t. Okay, so this is the Fourier transform. So this product, infinite product converges. So strictly speaking, I shouldn't write like this, but take limits. Okay, so for finite sums of independent random variables, it factors. What you have to do is that you have to take the, okay, you have to argue by taking limit, but that's an easy one, so I don't do that. A related point that I will just say here, that since cosine of, if you look at 1 minus cosine lambda to the n t converges rapidly to 1. When you want an infinite series, the term should converge to 0 rapidly. When you want infinite product, the term should converge to 1 rapidly. What is rapidly? It's a general fact. Okay, let me just say first, what is 1 minus cos lambda to the n t is just 2 times sine square of lambda to the n t by 2. Which is bounded by, this is anyway positive, by the way, this is between 0 and 1, or between minus 1 and 1. So this I'll just write less than equal to, sin x is less than equal to x, right? So it will be bounded by lambda to the 2n into t square by 4. So I'll just remove the 2 here. So it is bounded by this, and this is rapidly summable. Okay, so let me just state the fact about infinite products. Infinite products, so when you have product 1 minus an, so let us, in our case, it's actually true even with complex numbers. So let us say an's are between 0 and an's are less than 1 in absolute value. Actually, it's true even with complex numbers. Product converges. What do we mean by converges? It means you take the partial product up to capital N and take limit. That converges if and only if, converges absolutely if and only if summation mod an is finite. Okay, so rather, let me remove, I don't want to define anything. So converges, let me say, if summation an infinity. Also, another fact which will be useful for us, that in this situation, the product is strictly positive unless an equal to 1 for some So here let me write less than equal to 1 since cosines can also be equal to 1. Okay, so let me say mod n less than equal to 1 and I am taking actually real numbers. As I said, all this you can do with complex also, but for the purpose at hand, I don't need that. So this product not only converges, it is not zero unless one of the terms is 0. Okay, this is a simple fact. Let me even give the reasoning. It's easy. If you have not seen this before, why? You can do it two ways, equivalent ways. One way is you take logs and use the fact that log 1 minus x is log 1 minus x is minus x square by 2 minus x cube by 3 and dot dot dot. So you can convert it to logs and look at but it is mainly for ans are going to 0. That's how you think. I mean, anyway, the 1 minus an should go to, so we are having summation an finite. So ans are going to 0. This is to a large extent, you can say that it is approximately like minus x for small x. So that's why if you want the infinite product to converge, you want the infinite sum of the logarithms to converge, not go to minus infinity, for example. And that is equivalent to summation of the terms itself. Instead of log of 1 minus x, you just have that's more or less same as x. That's how these two are equivalent. So this is one way to see it. I mean, this is, yeah, let me leave it at that. So that's one way to see it. You can, in fact, this is equivalent sort of. So this is why this is rapidly convergent. This is like, this is converges rapidly. Summable over n for fixed t. Hence the product cos lambda to the nt converges. For all t in the real line. One can go further and say that it's in one uniform over compact sets and so on, but we don't need that. I mean, so we don't need all that. So converges for all t in R, and also as a byproduct of what I said here, I will say that, let me record it here, nu lambda hat of t is not 0 unless one of the terms is 0. When will lambda to the n t cosine will be 0 for some n? Unless that for that to be 0, cosine of something is 0 means it has to be an odd multiple of pi by 2, right? So unless lambda to the n times t is an odd multiple of pi by 2, that is, unless t is equal to, let's say, this is an odd multiple of pi by 2 divided by lambda to the n for some integer m and n greater than equal to 1. You know, the product is only from n equals 1 onwards. So n is from 1 onwards, m is any integer. So these are the only places where it can vanish. Other places it doesn't vanish. It's a point that will come in handy later. So this is the definition of Bernoulli convolution. Any questions? Anything not clear? Okay. Okay, so then let me go on. So what is it we want to know? Okay, so the main question, so let's see an example. Okay, so example, when lambda equal to half. What is lambda? What do you get when lambda is half? You can use any of these pictures if you like. What is it you get? What do you get? So epsilon 1 by 2 plus epsilon 2 by 4 plus epsilon 3 by 8 and so on. Yes, does anyone know? I mean, any of the students? What will be the distribution of that thing? So it is a fact that you see in probability class that nu lambda in this case is actually normalized Lebesgue measure on -1, 1. Okay, so you may have seen it more in 0, 1. The way it is usually taken is if you pick a random number, uniform random number in 0 to 1 and write the binary expansion, then the digits are independent Bernoulli random variables. So they are 0 or 1 with probability half each and independent of each other. So that is something you may have seen, right? Because so on 0 to half, the first digit is 0, and on half to 1, the first digit is 1. And then the second digit will divide each of these intervals into two parts. So it is 0 on the first half of both those intervals and 1 on the second half of both those intervals and so on. So that's how you get independence. So this is just going in the reverse direction. And instead of taking Bernoulli plus 0 and 1, which it is perfectly fine to do that also, it will be an equivalent thing. You can do an affine transformation from here to there. If you prefer 0 or 1, that is just you can get this epsilon by multiplying your Bernoulli by 2 and subtracting 1 or something. So it's an affine transformation of that. So if you are more happy doing that, you can, but it's the same thing. So nu lambda in this case will be normalized Lebesgue measure on -1, 1. So uniform measure on -1 to 1. Another one you may have seen is lambda equal to 1/3. So in this case, nu lambda is what is called the Cantor measure. On the standard Cantor set. Well, okay, it's not standard on -1, 1. I am taking minus standard Cantor set. You take usually 0, 1, delete the middle 1/3. Then in each of the remaining intervals, you delete the middle 1/3 and so on. If you have never seen the Cantor measure, it is okay. You don't need it. So, but Cantor set is if you have 0, 1, you delete the middle 1/3, 1/3 to 2/3. And then you delete the middle 1/3 in both and proceed like this. And what remains is a compact set, which is the standard Cantor set. Here, except that we have to do it in -1 to 1, and this is not 1/3, but whatever it is, the middle 1/3 is what you delete. Okay. So these are two examples which you may have seen before. So that's why I mentioned. Okay, so what is it that we are interested in? There is only one question we will ask about it. Okay, so the question that we will ask is nu lambda singular or absolutely continuous? Always to Lebesgue measure. I won't be saying with respect to Lebesgue measure whenever I talk singular or absolutely continuous with respect to Lebesgue measure on the real line. Okay, is it singular or is it absolutely continuous? This is the question. What we see is that this one is absolutely continuous. This is actually singular. Okay, so remember that singular means that there is a nu lambda puts all its mass on a set of 0 Lebesgue measure. That's what singular means. This is a set of 0 Lebesgue measure such that nu lambda of that set is 1. That is what singular means. Absolutely continuous means nu lambda has a density with respect to Lebesgue measure. Or the definition of absolutely continuous is that if any set has 0 Lebesgue measure, then nu lambda also gives 0 Lebesgue measure. It's the opposite, I mean, polar opposite of singular. And this is an important question about measures, whether they are singular or absolutely continuous. And so whether that's the same as whether it has density or not. Okay. Now, of course, not all measures are either, I mean, measures can be neither singular nor absolutely continuous. So it can be a mix of two. You can take half of Lebesgue measure plus half of Cantor measure. that one is neither absolutely continuous nor singular because of the Lebesgue measure part and the singular part. So generally, but here we will see that it will be one of the two. It will be either singular or absolutely continuous, and we will see what the answer is. But before that, let me settle the question for lambda less than half. Okay, so easy case. Nu lambda is singular. So if you didn't know Cantor measure or anything, whatever I said here, you will see the proof here. It doesn't matter. Cantor measure is the name given to the lambda equal to 1/3. So this will be singular. Okay. So for each lambda less than half, nu lambda is singular. So why do we say that? Okay. So let's write a proof of that. It's easy. This is easy part. See, let's look at x lambda, which is epsilon 1 lambda plus epsilon 2 lambda square. Let's cut it off at some epsilon n lambda to the n, and then it goes on further epsilon n plus 1 lambda to the n plus 1 plus dot dot dot. So let us look at the two parts separately. So I fix some n, fix an n, okay, and consider these two parts. Now there are two random variables here. This is one random variable, this is another random variable. Okay, so this one, what we can say, has absolute value. What is the absolute value of this? It is bounded by, you just put absolute values inside, and all epsilon i's have absolute value plus, I mean they are plus minus 1, so there is less than equal to lambda to the n plus 1 plus lambda to the n plus 2 plus dot dot dot, which is simply lambda to the n plus 1 divided by 1 minus lambda. Okay, so its absolute value. This is a small random variable in this sense. Here, what I want to do is, it's what kind of random variable is this? Okay, any guess? What do you want to do about this part? So this is a discrete random variable, right? Because each epsilon I has possible two values. So this can take 2 to the n distinct values. They are actually distinct, but if you want, you think at most 2 to the n. That's okay. It can take 2 to the n distinct values because each epsilon I is plus minus 1 and all of them will give rise to a different value. So you will have this 2 to the n distinct value. So what you see is that x lambda is one of these 2 to the n distinct values plus a number which has absolute value at most this. What this means is that the support of nu lambda is a subset of I sub j equals 1 to 2 to the n. It's a support of where each ij is an interval of length less than equal to lambda to the n plus 1 over 1 minus lambda, right? So you take each of these possible values around, actually the length is 2 times that because the absolute value is that. So for each point around this, you put an interval of length lambda to the n plus 1 over 1 minus lambda on each side. So its length is 2 times that. So it is a union of so many intervals. In other words, but what is the total length? So the total length is at most 2 to the n times 2 times lambda to the n plus 1 over 1 minus lambda. So the support of nu lambda is contained in an interval of this length. This is true for all n. Okay, so this goes to 0 as n goes to infinity because lambda is less than half. If lambda is strictly less than half, this goes. So implies that support of nu lambda has 0 Lebesgue measure. Let me just write length. If lambda is less than half. And that's what makes it single. Okay. Any questions about this? So the support of new lambda is has this much length. So it is actually it must be. I mean, support of new lambda must have zero length because it's less than this. The length of support is less than this for every n, and that goes to zero. So therefore it is. So we see that new lambda 0 less than, so on this one. So we see that it's actually singular here. Okay, 0 is not included, 1 is not included. Up to half, it is singular. At this point, it is absolutely continuous because that is itself Lebesgue measure. In fact, at lambda equal to half, what we get is exactly Lebesgue measure itself. So that is absolutely continuous. What happens in half to 1? That's the question. Okay, so, well, one exercise let me give. I mean, so just so that if you follow this, then it is not a hard exercise. So show that if half is less than equal to lambda less than 1, show that support of new lambda is exactly an interval, is the interval, in fact, is the interval minus 1 over 1 minus lambda to 1 over 1 minus lambda. So when lambda is half, that is minus, okay, lambda is half, it is, minus, no, something is wrong. Minus lambda over 1 minus lambda. So this is lambda over 1 minus lambda and minus lambda over 1 minus lambda. So when lambda is half, this is minus 1, 1. So this is exactly is equal to, okay. I'm not saying contained in or something. So by the way, support, you may remember what is the definition of support. It is important to keep in mind here because sometimes one may think, oh, this means that new lambda has the whole interval. So its support means it should be absolute. That's not what it means. Support means smallest closed set whose complement has zero measure. It's the smallest closed set whose complement has zero measure. So for example, just to give you an example, if you look at, if you enumerate all the rationals as R1, R2, okay, it's a countable dense set. And let me set nu equal to 1/2 at R1, 1/4 at R2, and so on. Okay, so then support of nu is the whole of the real line. Because it's supported only on rationals, you may say, but for us support is a closed set, smallest closed set whose complement has zero measure. So this one you cannot omit any rational number in your support. So you have to have all rational numbers. So the closure has to be the whole real line. So support being equal to an interval by no means says anything about it being absolutely continuous. Just I was making this point a bit explicit. Okay, so but this is an exercise. Show that, but show that support is this. No gaps are there. Okay. Okay, so any questions so far? I mean, at any time, please interrupt me. So if there are questions. So let me now show you that point that I mentioned that in fact, so it's possible for measures to, so remark, if nu is a measure on R, I mean Borel measure, finite Borel measure and all that, it is not necessary that it is absolutely continuous or singular. It could have both components. In fact, nu can be written the Jordan decomposition, or what is it called? Hand decomposition. What is it called actually? In fact, okay.
I think it's called Jordan Han, no?
Oh, is it? Okay. So Shrikant, I mean, what do we call it in probability? This.
Yeah, I think it is Han Jordan decomposition.
Oh, is it Han Jordan? Okay, okay, okay. I thought it was okay. I see. Oh, okay. So decomposition says that you can write nu as nu1 plus nu2, where this is absolutely continuous and this is singular in a unique way. So any measure can be written as an absolutely continuous part plus singular part. It's a bit like, but not, it's much deeper than that. You can write it as sum of a discrete measure plus a continuous measure. But actually, the singular part can be further decomposed into discrete one and a continuous singular part. So, whereas, so in general, everything can be written like this. Okay, so that is a fact. But what happens is that in our special case, however, this is called Jessen's law of pure types. It's more general than what we are saying here. Okay, I didn't say what is the more general setting, but nu lambda for each lambda in Z01, nu lambda is absolutely continuous or nu lambda is singular. One of the two. Okay, it's either absolutely continuous or it is singular. It can't be a mix of the two. So we'll prove this because it brings another property of this. The point of, you could actually, the more general thing that I was mentioning is more general Bernoulli convolution. You don't have to take this as exponentially decreasing. Okay, more general Bernoulli convolution, just to mention, you can also consider epsilon and an. Okay, where an's, so if you have taken basic probability theory course, you know that such a random series converges where if summation an square is finite. So this is the Khinchin-Kolmogorov theorem. In this case, Khinchin. If an is some L2 sequence, okay, let's say positive number such that summation an square is finite, then the random variable summation epsilon an converges with probability 1. So it is a Bernoulli convolution because it's a convolution of the first one, epsilon 1 a1 is a Bernoulli at a1 and minus a1 with probability half each. Second one is a2 and minus a2 with probability half each, and so on. Here, what we are doing is taking ANs to be very specifically an exponentially decreasing sequence. Okay, so we will not be considering more general situation, but those are also called Bernoulli convolutions. So Jessen's law, I think, is true at that level of generality, but yeah, for all those things. Yeah, but I am not. Go ahead.
One small point. I mean, sometimes one also divides this singular into like the discrete and the singular one. So
Yeah.
here it seems like you're going from a discrete to absolutely continuous at half to these singular measures. So
right.
there are like
Actually,
three
this will
transitions.
never have atoms. It's a good point. I forgot to say this. Okay. Another point which I can say is that, okay, maybe I put it in this exercise itself, just 1. 2 is show that nu has no atoms for any lambda in Z01, I mean. So it will never have atoms actually. This never has atoms. So it has only absolutely continuous part and continuous singular part. There is no discrete part. Okay, so this part is easy actually, that nu lambda has no atoms. You just look at this one can prove that. Okay, so let me leave it for a moment, and then but it could be, so that's why it eliminates the discrete part. So the atomic part. So now it could in principle be a mixture of the absolutely continuous and continuous singular part, but it is always going to be absolutely continuous or it will be singular. So you can write here it will be continuous singular because we already know that it is not going to have atoms. So does that answer your question, Shrikant?
Yes, that's nice actually.
Yeah, so this is the point. So this will be one of the two. Okay, so now let's see why. I mean, so why is this? For this, we go back to this. Like Cantor said, this has a very nice self because of the exponential sequence. This has a very nice self similarity property. Okay, so the proof is based on self similarity of what is the self similarity of mu lambda. So let X be distributed according to nu lambda. Is this notation clear to everyone? This means X is a random variable with distribution nu lambda. I don't know who are there. I mean, so any of the students, I mean, if I just assume that people are more familiar with probability, that's what I got the impression. So this type of symbol is okay, I suppose. X is distributed according to nu lambda, and let's say epsilon is plus minus 1 with probability half, and the two are independent. Then y equal to epsilon plus lambda x also is distributed according to nu lambda. Okay, if you multiply x by lambda and add an epsilon, you will be, because why? It's very trivial from the series form. Suppose I multiply, oh, okay, so I'm starting with lambda epsilon. So sorry, I should write here lambda epsilon. Lambda epsilon plus lambda times x, because if x is epsilon n lambda to the n, that sum. Now y will be epsilon lambda plus epsilon n lambda to the n plus 1. That's exactly the same form, right? Epsilon and epsilon n's are independent. So we are taking epsilon independent of the x. So this is exactly the same distribution. This is the self-similarity property. It's easiest to say in terms of easiest to write use random variables to write this kind of but this is a distributional identity. What we are saying is that you can writing it in terms of measures is a tad complicated. You have to introduce some notation. What we are saying is that if you take nu lambda, scale the measure down by lambda, okay, to an interval lambda, and then take two copies, one centered at plus lambda and one centered at minus lambda. Then you get a new measure and give half mass to both copies. So you'll get another probability measure that is same as nu lambda. That's how this is being said. But I hope the random variable language is easier to write. I mean, notation wise. So this is the self similarity of lambda. In some sense, nu lambda is composed of multiples of itself in some sense. So some scaled versions of itself. It has two scaled versions, since epsilon is plus 1 and minus 1, and lambda x is a scaled version of nu lambda. So so you can take two copies of nu lambda, scale down, and then reconstruct nu lambda. That's the self similarity. And the claim is this is the only measure that has this property. If nu lambda is the only one with this property. Only, let's say, probability measure with this property. Okay, why is that so? Let's prove that. There is no other measure with this same scaling property. Suppose nu has that property. of self-similarity with that parameter lambda. Like this, except that I don't have mu but mu lambda. That means, so that is x according to nu, epsilon according to plus minus 1 with probability half, independent, and y implies y equal to epsilon lambda plus lambda x also has distribution nu. That's what I'm assuming. Suppose nu is some probability measure with this property. Okay, so then let's look at nu hat of t. Okay, let's look at the Fourier transform of nu. It is just expectation e to the ity, right? Because y has distribution nu hat of t is expectation e to the ity. But what is expectation e to the ity? It into epsilon lambda plus lambda x. Now let's do the expectation over epsilon. If you want, it's conditioning on epsilon. It's independent of x. Epsilon takes two values, so you will get expectation of e to the it into lambda plus lambda x. That happens with probability half plus 1/2 expectation e to the it. Now epsilon is -1 minus lambda plus lambda x. Okay, so that makes it, what does that make it? So you just get e to the I, you see that expectation e to the it lambda x is common here. Okay, what are you left with? E to the I lambda t plus e to the minus I lambda t by 2, which is just cos lambda t. Cos lambda t times, this is again, x is again nu, x has distribution nu. So this is nu hat of lambda t. So you get this relationship for the characteristic function of nu, that nu hat of t is nu hat of lambda t times cos lambda t. Okay, so now iterate. Okay, I will leave out the limiting procedure. To get that, nu hat of t is product of cosine lambda to the n t. Because you will get here nu hat of, you will get cos lambda times lambda t times nu hat of lambda square t and so on. So you will get this. So implies nu hat is equal to nu lambda. Okay, so that's how we get this. So any questions here? So nu, this is the only measure with this self-similarity property.
Nu lambda hat, maybe in the last.
Oh, sorry, I wanted to write, yeah. So this is nu lambda. So the measures, the Fourier transforms agree by injectivity of Fourier transform, the measure is actually nu lambda. So now we get the distance law of pure types. Let me write the proof here. Let me leave part of it as exercise. Very simple exercise, nothing much. So write nu as nu1 plus nu2, where nu1 is absolutely continuous and nu2 is singular. So just argue that nu1 and nu2 have the same self-similarity property. They have the same self-similarity as nu. Just argue that. Okay, this part I will leave as exercise. Okay, it's a simple exercise, just nothing much to do, nothing really to do. All you need to know is that no absolutely continuous measure can be equal to a singular measure unless both are zero. Okay, so the zero measure is both absolutely continuous and singular, nothing else is both. So that's how you, anyway, so if both are, what this implies, these are not probability measures. So nu1 must be some a times nu, multiple of nu, and nu2 must be a times nu, b times nu. 1 minus a times nu. Oops, oh what happened? I didn't want to do this. Oh, how do I enlarge? By some, Zoom out. Oh, zoom in. Okay. Okay, I hope this is okay. So what you see is that this has to be actually this is one of them is 1 minus a times. Now you see that one of them has to be 0. Otherwise, if a is say let's say somewhere between, then nu is an absolutely continuous measure as well as a singular measure. That can't be the case. So this implies that a is 0 or 1. So nu is either nu1 or nu is equal to nu2. One of the two has to be vanishing. So that's the modulo of this point, that the two components also must satisfy the same self-similarity. You get this. So you get that from the self-similarity of nu itself. So there is no other measure with that. Okay. Any questions, comments so far? Okay. So now we come to the question. So what happens? So now we know that. So what is the, so what remains? So remaining question. What about nu lambda for, sorry, no, it's 0 for half less than lambda less than 1. Is it absolutely continuous? Singular? So what we saw was that up to half it was singular. At half it became absolutely continuous. Now beyond half what? It's the kind of question which if you come across in research, you naturally conjecture that, okay, you think that there are just very mild evidence. One is that the support is actually an full interval. It's not a 0 measure set. Also, you think that, okay, it was being singular, it became absolutely continuous, so it may stay absolutely continuous henceforth. That would be the natural thing to conjecture. Okay, so it turns out that's not true. So this is a mind-blowing result of Paul Erdős. So that there are countably many lambda in half to 1 for which nu lambda is singular. Okay, you have to complement it with another fact, which we will not go into, that for almost every lambda in half to 1, nu lambda is absolutely continuous. Okay, for most lambdas, it's actually absolutely continuous. But there are countably many exceptions. That's a strange thing. We will not do this part in red. We will not show this. That is, yeah, but we will do the first part as the application of Fourier analysis. Okay, so what tool do you have to show that nu lambda is singular? You have a measure. You want to show it's not absolute. I mean, it's enough to show it's not absolutely continuous, right? Because now you know if it's not absolutely continuous, it has to be singular. So how do you show something is not absolutely continuous? What tool do we have? Any suggestion? So what tool could we use to show that a measure is not absolutely continuous?
Maybe we can assume absolute continuity and use Radon Nicodemus theorem.
Yeah, but you will get something. But how will you get a contradiction? What we have a good handle on here is the Fourier transform. In terms of Fourier transform, what would you use to show it's not absolutely continuous?
Riemann-Lebesgue or something.
Exactly, Riemann-Lebesgue. So Riemann-Lebesgue is a necessary condition, right? Of course, if Riemann-Lebesgue fails, Riemann-Lebesgue says that if a measure is absolutely continuous, then its Fourier transform goes to 0 at plus minus infinity. So if you find that Fourier transform does not go to 0 at plus minus infinity, then you are done. It's not absolutely continuous. And in this particular case, then it forces it to be singular. Okay, so of course, if Riemann-Lebesgue fails, you have nothing to do. I mean, so Riemann-Lebesgue is not necessary. It's only a sufficient condition. So we'll use Riemann-Lebesgue, but for which lambda? What are these countably many lambda for which it fails? Here is this is where it gets really mind-blowing. So so nobody had thought of this thing. So Erdős came up with this whole business. So what are these exceptional lambda? So we will use Riemann-Lebesgue, but before that, I want to tell you what are these lambdas for which it fails. Okay. So for that, we need a little bit of things about numbers. Okay, so some definitions, Okay, so we will need what are these lambdas that are exceptions. So for that, I need to introduce a little bit of things from algebraic number theory. I mean, just definitions. So you may remember, so theta, so let's say theta is a number, theta is a real number, is called an algebraic integer if there is a polynomial, integer coefficient polynomial. Monic polynomial. What that means is something like x to the power p plus a1 x to the p minus 1 plus dot 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 plus up to a sub p. Okay, where ai's are integers. Okay, such that that vanishes at theta. See, not all numbers are roots of integer polynomials. In fact, there are only countably many integer polynomials, right? Because at each degree, there are only countably many possibilities for all these. So there are totally, if you take the set of all polynomials with integer coefficients, there are only countably many. And there are roots, finitely many roots for each one. So the total number of algebraic integers is countable. So obviously not all real numbers are going to be algebraic integers. So there are non-algebraic integers, but there are also algebraic integers. But we want specifically a particular type of algebraic integer, an algebraic integer theta is called a PV number. So this PV stands for piezo and Vijayaraghavan. So he was quite a well-known number theorist, Indian number theorist, Vijayaraghavan. He worked in Dhaka, I think, mostly. So it's a PV number if two things. One is theta is bigger than 1. Oh, okay. Before that, I should have said one more point. Okay, so maybe since I started the sentence, let me finish it. And all its conjugates, they're called Galois conjugates, are absolute of absolute value less than 1. Okay, what are these conjugates? I should have said that first. What are these conjugates? I should define that. So when you have such a thing, okay, if theta is algebraic, there is a unique polynomial of smallest degree whose 0 is theta, that has theta as a 0. Okay, there is a unique polynomial, so it's called a minimal polynomial. It's called the minimal polynomial of theta. Because the smallest degree, okay, you find first of all there is a smallest degree for which it works, and at the smallest degree you find, okay, yeah, so there will be a unique one because you will see that yeah, okay, there is a unique one. Why is that? Okay, maybe that's not clear, but it is true. So let me just say this. Okay, so it's called minimal polynomial of theta, and its other roots, the other roots of the minimal polynomial are the conjugates of theta. Okay. I mean, the word comes from the original conjugate. Complex conjugate is because x square plus 1, you call one root as I, the other root is minus I. That's like that. But here we are talking about real ones. So one example we can give is this famous one. What is that? Golden ratio. What's the equation for that? X square minus x minus 1 equal to 0, is it? What are its roots? 1 plus or minus square root of, is it this or b square minus 4ac plus or minus root 5 by 2, right? So there are two things, 1 plus root 5 by 2 let's call theta, and let's give it another name, tau. It's 1 minus root 5 by 2. Okay, this is the golden ratio, right? So this theta is bigger than 1 and tau is less than 1. Hence, theta is a Piso-Vijayagan number.
It's 1 o'clock.
Okay. Okay, so I didn't quite complete. So let me just complete by saying, so what are these countably many exceptions? So these countably many exceptions are precisely when these exceptional values are when lambda is 1 by theta, where now lambda is between half and 1, so theta will be between 1 and 2 is a PV number. Okay. So if you take the reciprocal of a Piso-Vijayagan number in 1 to 2, then it will turn out that that thing is actually for those numbers, nu lambda is actually singular. It's, I think, when I first saw it, it was mind blowing. I mean, why one would bring something like this into this game? Actually, I mean, how is the algebraic properties of a number? This is not what you would see if you are just thinking of measures and so on. But this is true that these numbers, and to this date, nobody knows any other exception. So it's a question, open question till now, whether these are the only exceptions in half to 1. We know that for most lambdas it works. But are there any other exceptions other than reciprocals of Piso-Vijayagan numbers? Nobody knows. It's open for 70 years now. So many people work on it. Anyway, so I will do the proof of this next time. Okay, and then go on to other applications.